For section 2.3, we're looking at polynomial functions and their graphs. A bunch of fun things in this section. To start off, what we'll be looking at is, first of all, identifying a polynomial function, and then we'll recognize characteristics of graphs of polynomial functions. We'll determine the end behavior based upon the degree of the polynomial. We'll use factoring to find zeros. We've already been doing that in some earlier sections, particularly with the quadratics in the last section. Identify zeros and their multiplicities. Use the intermediate value theorem. Understand the relationship between degree and turning points. And then finally, graph the polynomial functions using all of these techniques. First up, the basic definition of a polynomial. Now, a lot of people look at this polynomial formula and just kind of get overwhelmed by all the subscripts and exponents. They're like, ooh, well, all this is n is the highest power on x, and then it's saying every other x term is going to be a lower power. All of these coefficients, a sub n minus 1, all the way down to a sub 2, a sub 1, they're just some numbers. And showing that the numbers could be different, we're using different subscripts for each of the letters a. So it's saying if you have any number times x to some power plus any number times x to the one lower power all the way down to a constant, then this is going to be a polynomial function of degree n, where n is just the power of the highest powered variable in your problem. Now, of course, that n has to be some whole number. It can't be a fractional value or something, or then you have a radical expression as opposed to a polynomial function. Now, when we talk about the graphs of polynomial functions, what I need you to remember is that they're always going to be smooth and continuous. You can draw them with your pencil from left to right without ever having to stop to draw an open circle, a gap, an asymptote. Nothing like that ever happens. And any of the turning points are going to be smooth turning points. You're not going to have any abrupt, like absolute value scenarios where it forms a V. They're all going to be nice, smooth curves. So all polynomial functions, smooth and continuous. Now, the end behavior of polynomial functions is going to be based upon the degree of the polynomial. We can say that the end behavior is just its behavior as it goes off to the far left or far right. Although the graph of a polynomial function may have intervals where it's increasing and decreasing, the graph is eventually going to rise or fall without bound. So it's either going to go off towards infinity or negative infinity as it forever moves to the left or as it forever moves to the right. Now, this next little page here will show you the guaranteed end behavior in any scenario. So n is just the degree of the highest powered variable in your entire polynomial. We say, well, anytime that is an odd polynomial, like x cubed, x to the 5th, x to the 7th, could be x to the 25th. Well, anytime that largest power of x is raised to an odd power, then all you have to do is look at its coefficient. If its coefficient is a positive number, you're guaranteed the end behavior is going to be looking like this. It's going to start low and it's going to finish high. Whenever I'm trying to remember this, I just think of a positive x cubed. I know a positive x cubed starts low and it ends high. Similarly, when I look at the next case, I just keep in mind, well, all odd or all negative odd functions look like a negative x cubed in their end behavior. They're going to start high and they're going to end low. Now, if it's not degree 3, you could have a bunch of turning points on in between here. That's why we have the dotted line here showing that, well, there could be many turning points in between, but at the beginning, you know it starts high, and at the end, it's going to end low. Now, if it's a positive even function where that highest powered exponent is an even number, then you can say it's always going to start high and end high. And I just think of a y equals x squared in this case to remind me of that. Now, if it's not an x squared, but instead if it's an x to the 4th, an x to the 6th, an x to the 8th, you could have a lot of turning points in between, but in the end, it's going to start high and it's going to end high. For a negative even function, if a sub n is a negative number, and that's the coefficient of x to some even power, then you know your function is going to start going down and it's going to end going down. So we say it falls to the left and it falls to the right. Now, keep that in mind for the end behavior of any of these functions, and that's going to be needed in all of the problems in this section. Just to take a quick look at this one, now we have no idea the behavior on the x-axis yet for this problem. We're not worried about that. What I am worried about is just looking at this equation and say, okay, it's a positive x to the fourth. Every single positive even function in existence starts high and ends high. That's all I really need to know here. Now, from factoring that and setting the factors equal to 0, we can find where the x-intercepts are and the behavior at each of those x-intercepts. That's what we'll be looking at on the next few slides here. Zeros of polynomial functions. A 0 is going to be where it crosses the x-axis. 0 is another word for a root or a solution. So on this page, I say if f is a polynomial function, the values of x for which f of x is equal to 0 are called the zeros of f. The values of x are the roots or the solutions or zeros. All of those are synonyms of one another of the equation f of x is equal to 0. Each real root of the polynomial equation appears as the x-intercept of the graph of the polynomial function. Let's see that in action here. So in this one, I'm giving you an odd function. You say, okay, all positive odd functions will start low, end high. I know that that has to be the case. So this is going to look like a positive x cubed going on in through there. So I can say it's going to start low, end high. It's going to be pointing down in quadrant 3, pointing up in quadrant 1. Now, when I'm thinking about the x-intercepts here, I say, well, okay, the x-intercepts are the zeros. I have to set my function equal to 0 and factor. Anytime you have 4 terms, you should automatically think, ooh, factoring by grouping. I group the first 2 together and I pull out an x squared. I group the second 2 together and I pull out a -4. When I do that in either group, in the first group, when I pull out an x squared, I'm left with x plus 2. In the second group, when you factor out a -4, once again, you'll be left with x plus 2. So now the factoring by grouping technique says, well, the term in common is the factor x plus 2. What's left over when you factor that out? Well, x squared minus 4. Now, you could further factor this down and say, well, x squared minus 4 is the difference of 2 squares. It's going to be x plus 2, x minus 2. And so we're going to have the factor x plus 2 occurring twice, and then the factor x minus 2. I showed you didn't have to do that. As soon as you get it factored in any capacity, you can go ahead and set those factors equal to 0. X plus 2 is equal to 0, and x squared minus 4 is equal to 0. If x plus 2 is equal to 0, we move the 2 over and we have a solution of -2. But now if x squared minus 4 is 0, then x squared is 4. Principles of square root says we can take the square root of each side, but the side not containing the variable you're solving for has to be the positive negative square root of that side. Well, plus minus the square root of 4 gives me positive or -2. Now, please notice I had a -2 already. I'm getting a -2 as an answer down here as well. So -2 showed up as an answer twice, whereas positive 2 only showed up as an answer once. Now, notice how this graph is going to look on the next page. We knew it was a positive x cubed. All positive x cubed functions starts low, ends high. I knew it had an x-intercept at -2 and 2. Now, how do I know that it just touches and goes back in the direction it came from at -2, and it crosses right through at a +2? So how do we know that? If we don't want to depend upon a graphing utility to graph this for us, and I certainly don't want to depend upon a graphing utility, how are we supposed to know that? Well, because of our rules. Rules of what's called multiplicity. Multiplicity is just how many times a solution occurs after you factor. So in our last one, we had a solution of x equals -2 that occurred twice. That would be called multiplicity 2. Please notice it says anytime a root r or a 0r is an even multiplicity, that means the answer occurs an even number of times, then the graph is only going to touch the x-axis and turn around at that value of r where it has the x-intercept. Now, if you have an x-intercept or a 0 at a value of r that it's of odd multiplicity, then the graph is going to cross. So in our last problem, the solution 2 occurred once, and you'll see, well, okay, then you crossed right through the x-intercept at 2. But the x-intercept at -2 occurred here and here. It occurred a multiplicity 2 times. Anytime it's an even multiplicity, it's only going to touch at that x-intercept or at that 0 and go back in the direction it came from. Now, on this page, notice down here in the last portion, I say, regardless of whether the multiplicity of a 0 is even or odd, graphs tend to flatten out near zeros of multiplicities greater than 1. So the greater the multiplicity, the more exaggerated it's going to be flattening out at the x-axis at the point. And then it's either going to go back in the direction it came from if it's of even multiplicity, or cross through if it's an odd multiplicity. Let's look at this problem together. So here I'm asking you to find the zeros of f of x is equal to -4 times the group x plus 1/2 squared times the group x minus 5 cubed. Well, first of all, before I even find the zeros, I would like you to think about what the end behavior is. I know it's going to be a negative because -4 is multiplying the x terms. And then I would have an x squared times an x cubed. My leading term here would be a -4x to the 5th. All negative odd functions will start high and finish low. So I know that this function will start high, finish low, because every single negative odd function in existence does that. So, and remember, that's what we were talking about on this page right here. It's a negative odd function. So it's going to start high, it's going to finish low. Now it could have some turning points in between, and it will have some turning points in between. So now, when I'm thinking about the x-intercepts here, all I would do is set these factors equal to 0. X plus 1/2 is equal to 0. You're going to get a 0 at -1/2. X minus 5 is equal to 0. You're going to get a 0 at x equals 5. But please notice, I'm saying, okay, I set that function equal to 0, which means I set each factor equal to 0. The first one set equal to 0 is going to give me a solution of -1/2, like I mentioned on the previous page. But I also need to keep in mind, yes, it's that solution of -1/2, but it occurs twice. Why? Because it comes from a root of multiplicity 2. So that root, you could think of that as, hey, that's the group x plus 1/2 times the group x plus 1/2. Both of those factors you could set equal to 0, and both of them would result in the answer of -1/2. What does that tell me? It tells me that my graph is not going to cross at x equals -1/2. It's just going to touch and go back in whatever direction it came from, and we'll see that on the next page. Now, at x equals 5, I set the other factor equal to 0. I do get the solution of x equals 5, and I know that that 0, or that solution, 0 and a solution, remember they're synonyms, so that solution occurs 3 times. Well, what does that tell me? Anytime the solution is going to occur an odd number of times, it's going to cross through the x-axis at that x-intercept. And since it's of odd power greater than 1, instead of just crossing straight through, it will flatten out before it crosses, but it will cross. Just like the graph of y equals x cubed and how it goes through the origin. It flattens off a little bit as it goes through the origin, but it does cross. Now, let's look at the graph on the next page. So here's my original function, -4 times x plus 1/2 squared times x minus 5 cubed. I had my x-intercepts at -1/2 from this factor and at +5 from this factor. I knew that the end behavior was starting high and finishing low because it was a negative odd function. All negative odd functions start high, end low. So the first thing I would do when I graph this would just be drawing an arrow up and drawing an arrow down here. Now, the connecting points, we know it has an x-intercept at -1/2. It has an x-intercept at 5. Because the 0 or x-intercept at -1/2 occurs with multiplicity 2, it's just going to go down, touch at that point, go back in the direction it came from. Now, do I know precisely how high it goes? I don't, and nor do I need to know. All I'm really interested in is the behavior around the x-axis. Generally, the high point fits about right in between your two x values. So if I have an x-intercept at -0.5 and an x-intercept at 5, I expect it to hit a maximum value somewhere in between 2 and 3. So it's going to go up, hit a maximum somewhere around 2 or 3, then it's got to come back. How do I know it has to come back down? Because it has an x-intercept at 5. It has to. So it can't stay up high. Now, I know it has that x-intercept at 5, but instead of going back up again, it's of no longer even multiplicity, so it does not look like this. It's going to cross through it at 3. So anytime it's crossing but of greater degree than 1, it kind of slides through. So I drew that crossing with a sliding pattern that looks like a negative x cubed going through the origin, except this is shifted over to x equals 5. And then you can say it finishes up and you have the end behavior starting high, ending low, and the correct behavior at each x-intercept. Please do not belabor how high or low your curve gets in that. That's more of a calculus topic, because we can talk about when we take the first derivative of the equation, that's going to be when this function flattens out, because the derivative is, if you set the derivative equal to 0, it's going to find any x value where the slope at that point is 0. So it's no longer increasing, it's not yet decreasing. At the instant it hits that maximum value, the slope would be 0. And so you just say, well, all I'd have to do is set the derivative equal to 0, and it's going to find the location of any maximum or minimum points. So in other words, it's not for us to worry about in pre-calculus. That's something to concern ourselves with in the next class. The intermediate value theorem, it's really quite a simplistic theorem. And what I mean by that, let me go back to the previous graph. Let's say, for example, you didn't have the original function, but I was asking you to prove to me that there is a 0 somewhere, let's say, in between 4 and 6. We know that there is a 0 at 5 just by looking at the graph. What if I didn't have the graph, but I ask you to show me that there is a 0 located between 4 and 6? You'd be able to. How? Because you could plug in f of 4, and f of 4 is going to give you a positive value. Well, then if you plugged in f of 6 is going to give you a negative value. Well, if f of 4 is positive and f of 6 is negative, you know that for some x value in between 4 and 6, it's had to have an x-intercept. That would prove the existence of an x-intercept between 4 and 6. That's what the intermediate value theorem is saying here, guys. Please notice it says, if let f be a polynomial function with real coefficients, if f of a and f of b have opposite signs, so one's positive, one's negative, then there is at least one value c between a and b for which f of c is 0. So you can't go from a negative value to a positive value without there being some value in between for which the y value is 0. So it's impossible. And you think, well, why is it impossible? Because it's a continuous curve. You can't go from negative, 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 and then miraculously just start being positive all of a sudden. All of the points have to be connected. So we can say equivalently, the equation f of x equals 0 has at least one real root between a and b. Let's see that in practice. So I'm asking you to show that the polynomial function f of x is equal to 3x cubed minus 10x plus 9 has a real 0 between -3 and -2. Now, I'm not asking you to find the 0. In order to find the 0, you have to factor that expression, and that would be pretty troubling. That one's not going to factor easily. But I would say, well, in order to prove it with the intermediate value theorem, all I need to do is evaluate the function at -3 and evaluate the function at -2 and show that I get opposite signs for the y values there. That's what I've done down here. Evaluate the function at -3, plug a -3 into this function, and you can see I got a -42. All right, so I'd have the ordered pair -3, -42. Now, when I plug in the x value -2 into this function, I'll get the 3 times -8 is -24. Then I have plus 20 plus 9. I can say, well, that's going to be 29 minus 20. That's a positive 5. So I've went from -3, -42 to a -2, positive 5. You can't go from a negative y value to a positive y value unless for some x value in between -3 and -2, the y value was 0. So that's what I'm showing here on this page. Now, we do not have to find the specific x value. All we have to do in the intermediate value theorem is show that, well, since f of -3 gave us a negative and f of -2 gave us a positive, there is some x value in between -3 and -2 that gives us a 0. And I didn't actually label the x-intercept to show you where that 0 is at, just because that's not the point of the intermediate value theorem. It's just stating that this has to be the case. You can't go from a negative to a positive without, for some x value in between, having that x value with a y value equal to 0. Thus, the intermediate value theorem. And we'll have a few homework problems to follow up on that. Now, one of the easiest things as far as a polynomial is to think about how many turning points it has. The number of turning points, and here I'll just keep it simple and say, in general, if f is a polynomial function of degree n, then the graph of f has at most one less than that in turning points. So if I say, how many turning points does a cubic have? Well, a cubic is degree 3. So you would expect it to have 2 turning points, one less than the degree. Do all polynomials have 1 turning point less than the degree? No, but that's the most they could have. So if I have a polynomial degree 10, how many turning points could it have? Well, it could have 9. Now, whenever you're thinking about the number of turning points, this is telling you the maximum number of turning points. I could go further and say the other possibilities for those number of turning points always differ by 2. So a polynomial degree 10, it could have 9 turning points. That's the most it could have. But it could also have 7, 5, 3, or 1. All of those are options. What if you had a degree 7 function? How many turning points could it have? It could have 6 turning points. It could have 4. It could have 2. And degree 7 could have 0 turning points, like the graph of y equals x to the 7th. Looks pretty much just like y equals x cubed, that just goes right through the origin, sliding through, always increasing, never has a turning point. So when we talk about the most number of turning points, it's always 1 less than the degree. Now, a strategy for graphing polynomial functions, and these strategies are pretty general because it really depends upon the specific problem, what all you need to do to get involved with it. But the first step, you're going to have to do no matter what, the leading coefficient test. And remember, that's what we talked about on that page that had the yellow background. If you have an odd function that is positive leading coefficient, it's going to start low and finish high. An odd function with a negative leading coefficient will start high and end low. If you have an even function that's positive, it's going to start high and end high. If you have an even function that's negative, it's going to start low and end low. And again, I think it's easy if you just remember the graphs of positive and negative x cubed and positive and negative x squared to remember that end behavior. Now, for the next step, it's just saying find the x-intercept. So you got to be able to set your function equal to 0 and know where it's going to cross the x-axis. And then keep in mind the multiplicity as well there. So anytime you have a factor and you're setting it equal to 0, if that factor is going to occur multiple times, if it occurs an odd number of times, it's going to cross the x-axis at that value. If it occurs an even number of times, then it's going to touch the x-axis at that value. And I need to remember that the greater the multiplicity is, the more the graph is going to flatten out. Now, this is regardless of whether it crosses or touches. The greater the multiplicity, the more flattened out it gets at that value where the x-intercept is going to be. The other things you can do to help graph, and it's always wise to have the x-intercepts and y-intercepts for any function. So step 3 is, go ahead and find the y-intercept. That's always super easy. Unlike the x-intercepts, which can be troubling to find sometimes with the factoring, the y-intercept you find by just plugging an x value of 0 in and finding the y value. Sometimes you'll have problems that you can be aided by looking at their symmetry. If it's an even function like y equals x squared, it's symmetric about the y-axis. If it's an odd function like y equals x cubed, it's symmetric about the origin. Then we can also remember the fact of as far as the maximum number of turning points is always going to be 1 less than the degree. So if you somehow have more than that, then you know you made a mistake. Now, let's look at that in action with this problem. I'm asking you to use the 5-step strategy to graph 2 times the group x plus 2 squared times x minus 3. So the first thing I would want you to do here is understand that this is a polynomial degree 3. So that's what I'm saying. You need to determine the degree n. Well, I know the degree n is 3 because I would have x to the second times x to the first. X to the second times x to the first is x to the third. My leading coefficient is a positive 2. What do you know about every positive cubic function? We know they all start low and they all finish high. That's all I know about the graph of this thus far. I don't know the x-intercepts yet, so I don't even try that. I just know that it starts low, finishes high. Second step, you're supposed to find the x-intercepts. Well, this function is already factored for us, so that'll be easy. You just set your factors equal to 0. X plus 2 is equal to 0, and x minus 3 is equal to 0. X plus 2 set equal to 0 gives me a solution at x equals negative 2, but I know that that solution occurs twice because that factor of x plus 2, it really could be written as x plus 2 times x plus 2. Both of those would have a solution of negative 2, so we say the solution negative 2 occurs with a multiplicity of 2. Which means it's only going to touch at the x-intercept at negative 2. Now, the solution 3 only comes once, which will mean it will cross at 1. That's what I tried to show here. So I knew my function started low. I knew my function ended high. I know it's only going to touch at that root negative 2 that had multiplicity 2. And I know it's going to cross at the root of 3 that had multiplicity 1. So that's all I know from the multiplicities of the roots. Now, the thing I'm not so interested in here is a lot of students get stressed out by saying, well, how far down does this go? Do I need to use my calculator to? Nah, you don't have to do that. And again, as I've said earlier in this video, that's more of a calculus thing to do. We could take the derivative of this function, set it equal to 0, and it's going to find the location of any x value at which your function flattens out. And then you could plug it back in and find any maximum or minimum values. But for us, I'm interested in the end behavior and the behavior at the x-intercepts, not so much if you go down far enough. Now, one thing you can do to help graph it out and know how quickly it goes down is by finding the y-intercept. That's my step 3. We find the y-intercept by plugging a 0 into the function. So you're going to have 2 times 2 squared times a negative 3. That's going to be 2 times 4 is 8. 8 times negative 3 is negative 24. So now I know it's going to start low. It's going to go up, touch at negative 2, come back down. It's going to cross the y-axis at -24. Now, I was pretty certain that that wasn't the low point, though if you started going back up from there, I wouldn't care, because I don't necessarily care about the behavior of the graph other than what happens at the y-intercept, x-intercepts, and the end behavior. The end behavior, x-intercepts and y-intercepts have to be right. So you'll see I didn't even finish graphing this off down here. Now, we could go ahead and draw in a nice continuous curve, but the reason I'm saying I'm pretty certain it keeps on going down is because the maximum or minimum point, it's usually right in between your two x-intercepts. So if I'm going from an x-intercept of -2 to -3, I would expect the low value to be right at about +1/2 or +1. So it's going to keep on going down and then start coming back up. Now, whenever we think about step 4, I said, well, you might use symmetry to help. You can't use symmetry in this one. Why can't you use symmetry in this one? Because it's not symmetric with respect to the origin, and it's not symmetric with respect to the y-axis. So no symmetry to help us in this one. It will help occasionally. And then use the end behavior, intercepts, and additional points we graph to graph the function. So again, I'm not so interested in, you know, precisely where this low point is. I just want you to know the graph started low because of the end behavior. It went up, it touched at -2, you had a y-intercept at -4, it probably hits its low value right at about 1, and then it's going to go up and cross. Why does it cross at the x-intercept of 3? Because it was a solution only once. And then you say, well, then the end behavior continues on, that standard end behavior for a positive odd function. Now, step 5, just double check and make sure that the number of turning points is correct. Well, it's a function degree 3, which you would expect it to have 2 turning points. It's always the maximum number of turning points is 1 less than the degree. Well, it has 2 turning points. That's what I would expect. Now, it could have had 2 turning points or 0 turning points, like the function y = x cubed doesn't have any turning points, but it's either going to have 0 or, in this case, 2, and it has the 2, so there's nothing unexpected about that. Now, this will finish out the notes for this section. Please do try the homework solutions. Make sure you check against what I did as far as the problems out of the book, and let me know if I can help you out with anything. I'll be glad to. This is a fun section.